Okay, so today we're going to talk about one of the classic. It's a classic, simple harmonic motion example, and that's why it's called the simple pendulum, because the simple pendulum is an example of simple harmonic motion. So how does this work? Well, a pendulum swings through a circular path right through here. So let's say we got the pendulum set up right here, little green uh, mass at the end of this string here, and the string has a length L, okay? And so the mass is going to swing through here, get to the rest position, swing over and back. You did a simple pendulum in grade 11, but now we're going to take a much more mathematical look at this simple pendulum and see why it's called a simple pendulum, linking to simple harmonic motion. So let's take a look at the path of the mass at the end of the string from here all the way through to here. And I'm going to call that X. Now, it's not a straight line. It's what we call an arc length. And you probably have learned about this in math class, that by definition, a radian in it's a unit for measuring angle. A radian is defined by this equation right here, that the path length is equal to the length here, which is the radius, multiplied by the angle here that matches the path length, the arc length. All right, there's the arc length x. It's matched by an angle theta. When that theta is given in radians, not degrees, we have this equation here. X, the arc length, is equal to L, the radius, times the angle theta in radians. I'm sure you've learned about this in math class. So let's take a look at one of the forces acting on the mass. And one of those forces is gravity. And I've drawn it right there. Okay, I've drawn gravity right there. Another force acting on this would be, of course, the tension force. Tension would be acting on it as well. And those are the only two forces. So what we're now going to do is take this vector, which is the force of gravity acting on the mass at the end of this string in the pendulum, and we're going to break it down into components, because any vector can be described as the sum of two other perpendicular vectors. And that's what I've done here. I've broken this vector down into this side here and this side here. And the three of them, the entire force of gravity vector and its two components, form a right angle triangle. Now let's see how I got these angles in here. So first, we have the angle theta in here. This is a right angle right in here. And then over here we have the angle phi right in here. There's the angle phi. We know that theta plus phi has got to equal 90 degrees. They're complementary angles. So if I take a look, I can see two other lines here. I can see a line right there. It's black. And a line right here, which is red, which is one of the components of the gravity vector, force of gravity vector. That's 90 degrees in here. So if I've got theta phi here, that means the complement to phi has to be theta right in here. But then lo and behold, look, I can find another 90 degrees. Here is the red dotted line and the full force of gravity vector. So right along here and right along here, that's 90 degrees. So if that was theta, the complement to completing this 90 would be phi right in here. Right in here would be phi. There is another 90 degrees here, which means that that vector angle right in here, that angle right in there, I should say, is theta. All right. If you have to pause the video and go through it at your own pace, do that. All right. Now, that means through trig relations, I can say that this side right here, a component of the full gravity vector is opposite to theta. So this side right here will be mg sine theta. This side right here which is adjacent to theta, I can call this side right here mg cos theta. Now, this portion of the full gravity, force of gravity vector, this is what pulls the mass along the arc length. This component of the gravity vector right here is what works against tension and keeps the rope string tight. So what I can say is the following. I can say that mg sine theta, and I'm putting it in magnitude signs because I really want to talk about the magnitude right now, is the, oopsie, the restoring force. This is what brings this mass back to the rest position. It is what brings the mass back to the rest position. It is a restoring force. Okay, we've seen restoring forces before when we have studied simple harmonic motion. It's the very definition of simple harmonic motion, that the restoring force is equal to negative kx. We learn this to be from our Professor Hooke, that this is called Hooke's law. But Hooke's law only works when the restoring force is linear, a linear restoring force. All right, kids, take a look at this restoring force. It is not linear. It is sinusoidal. So therefore, Hooke's law and simple harmonic motion would not apply. It would not be a simple harmonic motion. It would be a more complex harmonic motion. Harmonic meaning it still swings back and forth, but it's more complex because the restoring force, look at it right there, the restoring force is sinusoidal, not linear. So let's take a look at this restoring force. The restoring force would be equal to mg sine theta. So the restoring force, now I'm only interested in the magnitude right now. The restoring force is mg sine theta. But hopefully you learned in math class that if theta is small. Now remember, we're dealing with theta in radians. So if you're going to do a little comparison here on your own, you make sure your calculator is in radians. If theta is small, we can say that theta is approximately equal to sine theta. For example, let's say you have a theta equal to 0.0872 radians. If you were to find the sine of 0.0872 radians, you would get it to be 0.0871. That's practically identical. Practically identical if theta is small. So because of that, we can make this jump here. Force restoring is equal to mg sine theta. And then we can say if theta is small, remember this is in radians, then this is approximately equal to mg theta. So basically what we're saying here is as long as you don't pull the pendulum over too far, right, your restoring force will be linear. But if you pull it over too much, then the restoring force becomes sinusoidal. Now, remember what we said at the very beginning of this video lesson, that there is a relationship between the arc length and the angle. So if I take this right here and I rearrange it, I get that theta is equal to x over L. So I'm going to use that right in here. Oops. Now that I've made the jump to almost equal to, I can just continue with equal to because these lines are equal. And I can put in mg arc length over the radius. So the arc length that the mass at the end of this string goes through, as long as theta is small. So this becomes our restoring force. And I can then say that the magnitude of the restoring force is equal to mg over L times x. So look, there is our linear relationship between the restoring force and how far you are away from the rest position. It's linear. It's not x squared. It's not x cubed. It's not 1 over x. It's not sine x. It's linear. And then we have this term here, which basically becomes the k from Hooke's law. There you have it. It becomes the k from Hooke's law. And we have now proved, since we've come up with this equation right here, we have now proved, since we've come up with this equation right there, that if you keep the angle small enough on a pendulum, it will be a simple pendulum because the restoring force will be linear, and therefore it is simple harmonic motion with the mass of the pendulum, the gravitational field strength, all over the radius, the length of the string, being the k function, the k value, I should say, in Hooke's law. Now, just to wrap things up, I want you to recall something. We already learned from simple harmonic motion that the period of an object undergoing simple harmonic motion, known as a simple harmonic oscillator, is equal to 2 pi times the root of m over k, where m is the mass of the object moving, be it at the end of a spring or the mass at the end of a pendulum, divided by k, which is the restoring force. But look what we have just discovered. Oopsie, let me fix that. Look at what we've just discovered today. Look at what we just discovered today. That instead of having k when it's a simple pendulum, it's mg over L. All right. Well, if you're dividing by mg over L, it's the same as multiplying by the reciprocal, the inverse. So we get 2 pi L over G. So by remembering what we learned for a simple harmonic motion in the past, I can now tell you that the period of a simple pendulum is equal to 2 pi times the root of the length of the pendulum divided by the gravitational field strength near the surface of the Earth. So this is one of those classic examples that you'll see that all physics students have gone through of a simple harmonic motion being the way to describe a simple pendulum. Now in grade 11 we learned about this and we did a very qualitative uh, lab of this, but we never got into this mathematics because you didn't have the ability back then. Now you do. So we've proved why it is a simple pendulum, because if the angle is small enough, it's a simple harmonic motion question. So um, look, I've asked you to somehow hand in your chapter 3 assignment. We're going to learn how to do it. I've thought maybe you could take a picture with your camera. I don't know. I've created a little Dropbox area where you could attach your picture file. Maybe there's a better way to do it in D2L. I don't know. You kids are a lot smarter than me than I am at all this computer stuff, this online stuff, this digital stuff. Okay, so maybe you can help me. Anyway, that's my main goal today. Get that chapter 3 assignment handed in, and then we'll take it on to more work on chapter 4 tomorrow. And everybody take care, stay safe, wash your hands, social distancing, stay home, and we'll get through this. Okay, bye-bye.